When we think about climate change, we tend to think about carbon dioxide in the atmosphere warming the planet. Carbon is so central to our thinking about the climate that many other important aspects are excluded from the conversation. One of these things is water. Water is actually the dominant greenhouse gas, but its global effects are difficult to measure because it doesn't spread out evenly in the atmosphere like carbon does. Its effect on temperature also depends on the many forms it takes. When it takes the form of a haze, it has a warming effect. When it takes the form of clouds, it has a cooling effect, except for at night, in which it has a subtle warming effect. Since atmospheric water is hard to model, it tends to get ignored. But temperature is not the only important aspect of the climate here. If the climate can be warm or cold, the climate can also be wet or dry. The rampant rise of floods and droughts of our time are said to be caused by climate change, but really they are climate change. While temperature does have some effect on rainfall, floods and droughts are primarily caused by disruptions to the hydrological cycle. We tend to think of the water cycle this way. Rain falls, water evaporates, condenses into clouds, and repeats. But this is only part of the picture, since a lot more happens underground. Healthy soil is like a sponge that soaks up a lot of water. Some of it is taken up and stored by plants, and some of it percolates deep down into aquifers. This groundwater wells up and feeds springs and streams, which allows even more life to thrive. There's then much more water to evaporate from the saturated ground or to transpire through plants. This abundance of water vapor allows for more consistent rainfall. So what happens if we cut down the forest, plow the grasslands, and expose the soil? Without trees or plants to buffer the rain, the heavy downpour compacts the soil. The water can't soak down into the compacted ground, so almost all of it stays above ground and we have a flood. Almost all this water runs off, carrying loads of topsoil with it. And when the rain stops, the little water there is left evaporates very quickly, leaving the ground compact and dry. This lack of percolation depletes the groundwater over time, so it can't feed the streams, which dry up. Now there's no water in the land to feed rain clouds, and we have a drought. If a rainstorm does come, it just creates another flood and worsens the subsequent drought. Instead of consistent rainfall, we have a flood-drought cycle. Fortunately, it is possible to reverse this trend. There are ways to regenerate ecosystems and restore the water cycle pretty rapidly while feeding people in the process. Making subtle changes to the land's topography can slow the flow of water, allowing more of it to soak into the ground and be used by plants. Plants with deep roots help break up the compacted soil, allowing water to percolate deeper. Everyone has a place in reversing the climate crisis. Whether you're working to protect healthy ecosystems, regenerate damaged ones, or just helping yourself or your neighbor depend a little less on industrial agriculture, you are helping the earth heal.
In my youth, we learned in school that it takes 500 years to build an inch of topsoil. But there are people who are doing it 500 times faster than that. And if these practices were adopted on a global scale, according to some estimates, it could offset all emissions. We could begin drawdown, like right now. But we'd sacrifice agricultural productivity, right? No. Actually, these methods can be as productive or more productive than chemical-based agriculture. There's two things, though, that they do require that represent a profound shift in our agricultural system and our entire society. The first is that they are more labor intensive. In the United States, approximately 1% of the population is directly engaged in farming. That might have to go up to 10%, as it was in 1950. And maybe if you include gardens, maybe go up to 50%. And the other is that in regenerative agriculture, what works in one place may not work on another continent or even in the next valley over. The only way to make them work is to be a patient, attentive observer of that particular land. So it requires an ongoing intimate relationship that is unique between the human interacting with that land and the land itself. That does not fit into an industrial model. The essence of industrialization is standardization. That's what makes it efficient. That's what allows a machine to do it. In order to have a truly regenerative agricultural system, we have to undo that way of thinking. And that's another reason why we would need more people in close relationship to the land.
Regenerative agriculture is a set of farming practices that increase biodiversity in soil organic matter. Currently, most agricultural practices are devastating to biodiversity. Even organic agriculture, while not as bad, still does more harm than good. Regenerative agriculture is a way to reverse this trend to actually make a positive impact on the land. So what does regenerative agriculture actually involve? Answering this question is actually pretty tricky, because the practices that work best largely depend on the land that's being worked with. So the variety of different practices border on infinity, a bit more than this video can cover. However, let's look at 3 common forms that regenerative agriculture can take. The soil is full of organisms which are helpful for plants. Some convert soil nitrogen into a plant-usable form. Some bring water to the plants that would otherwise be out of reach. Others loosen and aerate the soil, increasing water absorption and allowing plant roots to penetrate deeper. When soil is turned over by a machine, most of these organisms are killed, so the crops must rely on chemical fertilizer, which ends up leaching into the water. Central to no-till farming is to not do that. Instead of tilling, plant cover crops whose roots break up the soil. Let the worms aerate the soil and bring down nutrients. Keep the soil covered with an organic mulch, which will break down over time, adding more organic matter to the soil. From the release of methane to clearing forests for pasture land, cattle raising is known for being very environmentally destructive. But this is not inherent to grazing animals. If the right practices are put in place, enormous amounts of carbon can be sequestered into the ground, soil can be built, and even desertification can be reversed in a matter of years. Here's how it works. The growth of grass tends to start slow, accelerate, and slow down again. This middle area is where it accrues the most biomass the most efficiently. If it's eaten before it gets to this point, its growth will never speed up. This is what happens with traditional pastured animals. They eat all the grass, which doesn't have the chance to grow back fast enough before getting eaten again, and we have overgrazing. This leads to soil erosion, drought, and desertification. But if the animals are kept in a tightly packed herd, like they used to be in nature, the grass has time to grow before being eaten. All that biomass in the grass is carbon that comes from the air. Not all of the grass gets eaten, however. Some of it gets pooped on and trampled, which ends up creating the perfect conditions for new topsoil to be built. This ends up happening incredibly quickly. This is one of the most complex and location-dependent practices there are. I will therefore be overgeneralizing a bit. It always starts with observing a local forest and the relationships between everything in it. The plants, the animals, the fungi, the landscape, the soil, the water, and then recreating these relationships in a way that's just as ecologically resilient, but produces more food. Food forests are often thought of as comprising 7 layers: the root layer, the ground cover layer, the herb layer, the shrub layer, the low tree layer, the high tree layer, and the vine layer. Every one of these layers either produces some sort of food or medicine, or is in some way helpful to the system as a whole. The plants are mostly perennials and include as many native species as possible. These 3 examples of regenerative agriculture, plus all the rest of them, all have something in common. Whereas in conventional agriculture, you seek to create as many of one thing as possible, in regenerative agriculture, you seek to create as many relationships between things as possible. You are one of those things. What sort of relationship with the land do you want to foster? Peas, beans, and clover are among the 18,000 species in the pea family. Most species in this family, including these 3, are known as nitrogen fixers. They increase the level of nitrogen in the soil, which plants need to produce protein so they can grow, and chlorophyll so they can photosynthesize. One way to use this in the garden is to interplant nitrogen fixers with other plants that need a lot of nitrogen. Or you could plant a nitrogen-fixing cover crop like clover for fertile soil next year. Okay, this can be useful, but doesn't nitrogen fertilizer do the same thing but more conveniently? Why bother with this nitrogen fixation thing? Understanding this requires us to understand how nitrogen fixation works, which in turn requires us to understand the broader nitrogen cycle. So let's start with the big picture. Nitrogen makes up 78% of the Earth's atmosphere by volume. But most of this nitrogen takes the form of 2 nitrogen atoms strongly bonded together, which isn't very reactive and is useless to plants. For it to become plant available, we need the help of bacteria. Various species of bacteria eat atmospheric nitrogen and poop out ammonium. This gets eaten by other kinds of bacteria, which poop out nitrite, which gets eaten by yet another kind of bacteria, which poops out nitrate. All of these forms of nitrogen are available for plants, especially nitrate, which is the easiest for plants to use. Plants can take this up directly if it is near their roots, but they most often rely on strands of fungi that attach to their roots and bring nutrients to them in exchange for the sugars and carbohydrates the plant roots exude. Dead plant material is also rich in nitrogen, and gets brought down with the help of worms, whose poop is a delicacy among nitrifying bacteria. Some of the ways nitrogen exits the soil is when the crop is harvested, when water carries it away, or when it becomes gaseous and returns to the atmosphere. Or if the soil lacks oxygen, different anaerobic bacteria grow, which convert nitrates back into atmospheric nitrogen. Notice that these things only happen with loose nitrogen in the soil, not with nitrogen inside organisms. Okay, so we know that the nitrogen cycle depends heavily on life in the soil. Without them, the plants would be quite sad. But you may have noticed, if the fixation process is done by bacteria, where do nitrogen-fixing plants fit into this? Believe it or not, nitrogen-fixing plants don't fix nitrogen. Rather, they create habitat for the bacteria that do. The roots of this clover plant have little nodules that house huge amounts of nitrogen-fixing bacteria. The ammonium that these bacteria create slowly releases into the soil for neighboring plants and microorganisms to use. When the plant dies, the bacteria disperse into the soil, resulting in an abundance of bacterial allies for future plants' nitrogen needs. You know how earlier I said that water can carry soil nitrogen away? This nitrogen ends up in rivers, which can disrupt the ecosystem by enabling algae to dominate. But remember, this only happens to loose nitrogen in the soil, and not to nitrogen embedded in organisms. And fertilizer adds pure nitrogen without the organisms. So when it rains, huge amounts of it run off and pollute the water. Loose nitrogen molecules are also much more prone to volatilization, releasing huge amounts of nitrous oxide, a potent greenhouse gas, into the atmosphere. But that's not all. Such quantities of pure nitrogen irritate earthworms, which end up dying or leaving. It disrupts the helpful fungus on plant roots and changes the soil pH, making it inhospitable to bacteria. In short, it kills the soil. When the nitrogen all gets used up or washes away, the organisms aren't there to help the plants get more. So now you have to add more fertilizer, which worsens the problem. And these organisms did much more than just supply nitrogen. The root fungi also brought up important minerals for the plants. And now that they're gone, mineral fertilizer must also be used. Instead of working with this self-sustaining web of organisms freely sharing nutrients, we have to spend more money to add loads of fertilizer to dead soil, poisoning the water and contributing to climate change. Considering the inability of dead soil to supply plants with nutrients, it's no wonder that throughout the last century, vegetables have been steadily declining in nutritional value. Healthy food requires healthy soil. So if the soil around you is rich and alive, try to keep it that way. But if, like most of us, the soil around you is dead or dying, nitrogen fixers can help to add a little more life so that someday our tiny allies under our feet will come back.
Most of the conversation about carbon today is about fossil fuel emissions. And most of the energy of environmentalists, in the climate movement especially, is to find ways to reduce carbon emissions. What has been left out of the conversation to a large extent, not entirely, is the role of forests and wetlands and soil in sequestering carbon, taking carbon out of the atmosphere, and restoring a healthy carbon cycle, where whatever carbon is produced, it is reabsorbed again. What I have learned is that the contribution of land use changes to atmospheric carbon is at least as much as the contribution of burning fossil fuels. Exposing soil to oxidation puts tremendous amounts of CO2 into the air, and the ruin of the biological systems prevents that released carbon from being brought back into the soil. When trees and grass and other plants uptake carbon from the air, a lot of it goes underground, taking the form of organic compounds, which means carbon-containing compounds that form soil. And that stay underground could be for a year, could be for a decade, could be for 100 years. Some of them are deeply sequestered in the soil. So they're constantly pulling carbon out of the air and putting it underground. So much so that carbon dioxide levels in the atmosphere have been rising slower than would have been expected in models that are based on how much we're emitting. The reason that they increase slower than expected is because the more that there is in the atmosphere, the more the plants take up. Of course, they're not increasing their uptake fast enough to offset emissions, but it points to the capacity for life to maintain atmospheric balance if we're not getting in the way. Unfortunately, we're getting in the way. Today, I think we have something like half of the trees that we had before civilization. Half of the mangrove swamps of Asia have been destroyed. 80% of the seagrass meadows on the New England coast are gone. We have rising emissions, and these organs of Gaia that maintain a healthy carbon cycle have been destroyed. So what are we going to do about it?